Welcome to this explainer. Today, we're diving into the incredibly fascinating and rapidly escalating engineering battle required to squeeze every last possible drop of oil from the Earth. You know, when we think of energy production, we usually focus on finding the oil or refining it. But the actual physical process of getting it out of the ground? It is literally a war against geology and physics. It's a wild journey that takes us from deep, ultra-high-pressure underground environments all the way up to some seriously complex surface mathematics.
Now, a lot of people picture an oil reservoir as some giant, cavernous underground lake just waiting to be pumped dry. But actually, scratch that. That's a total myth. We really need to think of the reservoir more like a giant solid rock sponge. The hydrocarbons are trapped right inside the tiny microscopic pores of that rock. So today, we're going to explore exactly how engineers wring that rock sponge out drop by drop using increasingly extreme and sophisticated methods as the well gets older.
Here's a quick roadmap for today's explainer. We're going to cover primary recovery, artificial lift, secondary and enhanced recovery, surface separation, and finally, forecasting the future.
All right, let's jump right into Section 1, Primary Recovery and Natural Flow.
So let's look at this first stage, where the Earth is basically doing all the heavy lifting for us. This inherent energy isn't magic, right? It comes from very specific natural mechanisms locked deep underground. When a well is newly drilled, the hydrocarbons often just flow naturally to the surface without us having to actively pull them. Why? Well, think of shaking up a warm bottle of soda and then popping the top. That's exactly what a solution gas drive is doing, pushing fluids up. Other times you might have a massive gas cap expanding from above, a natural water drive pushing really aggressively from below, or even just gravity draining the oil down into the wellbore. In this primary phase, the reservoir's own geology is doing all the hard work.
But as you can probably guess, that natural pressure doesn't last forever. That brings us to Section 2, the power of artificial lift.
Eventually, that natural pressure drops off. The underground sponge basically stops dripping on its own, and engineers have to step in to keep those hydrocarbons moving. And here we have our two main physical tools for artificial lift. On the left, we've got the iconic Pumpjack, also known as a beam pump. You've definitely seen these silhouetted on the horizon, just nodding back and forth. They're sucker rod pumping systems that convert surface rotational motion into a reciprocating up and down motion. They are absolute workhorses for lifting fluids out of low-pressure mature wells. But on the right, what if you're in a super demanding offshore environment, or you just need to move a massive volume of liquid? That's where electric submersible pumps, or ESPs, come into play. These are multi-stage centrifugal pumps sent completely downhole and powered by a massive electric cable. It's a totally different approach for a completely different environment.
Now, if we don't want to use physical mechanical pumps at all, we have another incredibly clever trick up our sleeve: gas lift systems. Instead of pulling the oil up with a pump, we inject compressed, high-pressure gas down into the well, specifically into the casing tubing annulus, which is just the empty space between the well's outer pipe and the inner tube. Through special downhole valves, this injected gas aerates the fluid column. Imagine blowing air through a straw into a thick milkshake. It drastically reduces the density of the fluid, making it much lighter and frothier. Because of that, whatever bottom hole pressure is still left is suddenly enough to push that oil all the way up to the surface.
Moving right along, let's hit Section 3, Secondary Recovery and Water Flooding.
So eventually, even the best artificial lift techniques are going to hit a wall. When simple lifting just isn't cutting it anymore, we have to escalate our tactics and literally push the oil from within the reservoir itself. We've exhausted Step 1, now for Step 2. Secondary recovery brings in water flooding. Engineers stop just pulling from the producing well. Instead, they drill dedicated injector wells right nearby. Then they inject massive amounts of specially treated water deep into the earth. And this does two vital things. First, it completely repressurizes the depleted reservoir. Second, it creates a literal physical wall of water that sweeps the remaining crude oil through those microscopic rock pores, pushing it directly toward the producing wells.
But what happens when even that wall of water isn't enough? Welcome to Section 4, Enhanced Oil Recovery Techniques.
When water flooding can't reach the oil that's stubbornly clinging to the rock pores, we move to Step 3. This is where we get into the really advanced stuff, actually altering the chemical and physical properties of the oil itself. Let's look at two radical enhanced oil recovery methods here. On the left, we have CO2 injection. We inject supercritical carbon dioxide into the reservoir so it actually mixes with the trapped oil. This is called miscible flooding. It reduces the oil's interfacial tension and viscosity, essentially washing it free from the rock. On the right, we have thermal EOR. We use this for heavy, thick oil that normally flows like cold molasses. By injecting high-temperature steam right into the reservoir, we drastically lower the viscosity of the heavy oil. We're essentially melting it underground so it can finally flow toward the production wells.
Okay, let's head back up to the surface for Section 5, Separation and Water Management.
Because what actually comes out of the wellhead? It is never just pure oil. It's a totally chaotic, raw mixture. So we have to neatly separate this stream into 3 distinct phases: oil, gas, and water. We do this inside massive surface production vessels called 3-phase separators. Honestly, it's an exercise in physics and patience. It uses gravity segregation, allowing the heavier water to sink, the lighter gas to rise, and the oil to float right in the middle. It utilizes strict retention time to give the fluids the time they actually need to settle out. And to help the whole process along, the vessels employ complex internal baffles and weirs to physically guide and divide the flow.
We also have to deal with the massive amounts of extracted formation water that comes up alongside the oil. You can't just dump it, right? This produced water has to be rigorously treated to remove any trace of residual oil, solids, and scale. Once it's properly treated, the industry operates in a tight loop. This water is either re-injected right back into the earth to maintain reservoir pressure for the water flooding we talked about earlier, or it gets recycled for other operations like hydraulic fracturing.
Finally, we've made it to Section 6, Forecasting with Decline Curves.
So as engineers are squeezing out every physical drop they can, they also have to look to the future and predict exactly how long this well can survive this escalating battle. And reservoir engineers don't just guess, they use incredibly rigorous mathematics. Through decline curve analysis, they utilize 3 distinct mathematical models: exponential decline, harmonic decline, and hyperbolic decline. Because production doesn't just stop overnight, it tapers off in some really complex ways. By mapping current and past production data onto these highly specific mathematical curves, engineers can reliably forecast future production rates for months or even decades to come.
And that brings us to the final mathematical endpoint. The ultimate goal of all those decline curves is calculating the EUR, the estimated ultimate recovery. This is the absolute final metric of success. It calculates exactly how much total oil we can extract before the well reaches the very end of its economic and physical life. It's the ultimate bottom line that tells us if all the pump jacks, the water floods, and the steam injections were technically and economically worth the fight. And understanding this bottom line is absolutely crucial because it directly impacts everything from our everyday energy costs to the global management of finite resources.
We've journeyed from the natural, almost effortless flow of a brand new well all the way to injecting supercritical CO2 and doing complex hyperbolic math just to keep a mature well alive. When you think about the relentless, incredibly complex engineering required just to maintain today's production, you really have to ask yourself, how far will technology have to go to squeeze out those very last drops tomorrow? What extremes will engineers have to go to next? Keep questioning, keep learning, and thank you so much for joining me on this explainer.